Now we begin to talk about quantifiers, which allow us to make more souped up versions of logical statements. So we're going to have two quantifiers, the universal quantifier, which we'll talk about first, and then the existential quantifier. So for the universal quantifier, we have this notation. So suppose that we have a set S, which has a bunch of elements, perhaps even infinite set. Could be infinite, could not be infinite, doesn't really matter for this purpose here. It's a set of elements. And suppose that P of X is a statement or open sentence, right? So as we've seen, P of X, meaning it's a statement or open sentence that contains a variable inside of it. Now consider the statement, P of X is true for every element of S, right? That's a statement. It's claiming that this thing, P of X, this is true for every element of S, of the set. In other words, what are we saying? We're saying is P of X comma 1, and P of X comma 2, and P of X comma 3, and dot, 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 right? So in other words, we're saying P of X applies to every element of the set. So that's, this is an idea, not a incredibly exciting idea, but what we can do with, what we have for this is a new notation. I'm sorry, and this X should be lowercase, okay. This can be written as follows. For all X in S, P of X. Okay, so you read this as for all X in S, for all X in S, P of X. So this is saying again that P of X applies to every element of S. Now, is this new statement here true or false? So if P of X is indeed true for every possible choice of X from set S, then the statement for all X in S, P of X is a true statement. Otherwise, it is false. In other words, if it is not true for all possible values of X from the set, maybe it's true for some, but maybe not, but not for all. In that case, this statement that for all X in S, P of X, that is a false statement, because this statement claims that it is true that P of X is true for every element of the set. So for example, let's say we have this following set. Let S equal the set of all 2 times n such that n is an integer. Okay, so think about what this set represents. What are the elements of this set? So this is take every integer and multiply it by 2. So what you'll end up with is the following set. So it's an infinite set. It's the set of all even numbers, both positive and negative. By the way, 0 is an even number as well. So this is the set of all even numbers. That's S. Let's define the following open sentences. So E of X means that X is even, and P of X means that X is positive. Okay, let's just define those things to mean that. So let's say we say the following. Let's say we say for all X in S, E of X. For all X in S, E of X. So what that says is for every X in S, X is even. In other words, every element of S is even. Question, is it true? Is this statement that for all X in S, E of X, is that a true statement? It is. Well, here's the thing. E of X, this open sentence E of X, is true for every element of S. Therefore, the statement that for all X in S, E of X is a true statement. Now, another statement. Suppose we say for all X in S, P of X. So what that says is for every X in S, X is positive. Or in other words, every element of S is positive. Now, if we consider P of X, is it true that P of X is true for every element of S? It is. Well, actually, no. Sorry. P of X is true for some elements of S. Well, we see that it's true for like 2, right? And 4 and 6 and so on. But it's not true for some other elements of S, right? It's not true for 0. 0 is not positive. It's certainly not true for -2 and so on, going in the negative direction. So P of X is true for some elements of X, right? It's true for 2 and so on, but it's not true for some others. So it's not correct to say that P of X is true for all elements of S. It is not true for all elements of S. It's true for some, but not for all. So the statement that for all X in S, P of X is a false statement. Now we talk about the existential quantifier. So again, suppose we have a set S containing elements x1, x2, x3, and so on. And suppose P of X is a statement or open sentence. Consider the statement, the following statement. P of X is true for at least one element of S. So we're not claiming that it's true for all elements. We're just claiming it's true for at least one element. Maybe 1, maybe 2, maybe 15, at least one element. In other words, what are we saying? P of X comma 1, or P of X comma 2, or P of X comma 3, or dot, dot, dot. Right? We're saying that P applies to, well, at least one of the elements of the set. This can be written using our new notation, this is the existential quantifier. This can be written as follows. There exists an X in S such that P of X. So again, the way you read this is, there exists an X in S such that P of X. Now, how do we know whether this statement is true or not? If P of X is true for at least one X from S, then the statement, there exists an X in S such that P of X is a true statement. Otherwise, the statement is false, meaning if P of X is not true for any of the elements of S, then this statement is false, because this statement claims that P of X is true for at least one element of the set. Here's an example. So let S be the same set as before, set of all even numbers. Let E of X stand for the X is even, P of X stands for the X is positive. So what do we say? What does this say? This says there exists an X in S such that P of X. In other words, there exists an X in S such that X is positive. Or in other words, at least one element of S is positive. Is this true? Yes. Not all the elements of S are positive. However, at least one of them is. P of X is true for at least one element of S. So the statement, there exists an X in S such that P of X is a true statement. Now consider not P of X. So what does that say? That says that X is not even. Okay. Now, is that true for all elements of S? Is it true? I'm sorry. Is it true for S? Start again. Is that true for at least one element of S? Is it true for at least one element of S that element is not positive? It is true for at least one element of S because, for example, -6 is not positive. Therefore, this statement is true. There exists an X in S such that not P of X. There exists an X in S that is not positive. Another example, consider E of X. So E of X says that X is even. And the question is it true for at least one element of S? Answer is yes. In fact, it's true for all the elements of S. It is true, but at the very least, it's true for at least one element of S. In fact, it's true for all elements. So this statement that there exists an X in S such that E of X is a true statement. Now consider not E of X. That says X is not even. Is that true for at least one element of S? In other words, is there one or more elements of S that are not even? No, it is not true for any element of S because all the elements of S are even. So not E of X is not true for any of the elements of S. So the statement, there exists an X in S such that not E of X is false because this statement claims that there is an element of S that is not even, but we know that that's not true. So this statement is false. Again, this here is not a statement. It's just an open sentence because it depends on the value of X. But this thing here is a statement because it's claiming something about S, and it's claiming that something applies to at least one element of S. Now we know that the statement is false. Okay, now we have to talk about translating from English to logical notation. So you'll see often sentences written in math or in other contexts written in English, and it's sometimes useful to be able to translate them into logical notation. So here are some examples. So we start with the first example. So we're going to go English and then logical notation, and then say whether it's true or false. So here's the first one. There is an integer that is not even. The way you express that in logical notation is something like this. There exists an n in Z, right? So there's an integer n such that not n is even, right? So there is an integer that is not even. Is that statement true or false? Well, it's true. There are many integers that are not even, but at the very least, there is at least one, right? So for example, 3 is an integer and it is not even. So this statement is true. Next statement, every integer that is not odd is even. Okay, how do we express this in logical notation? So here we use the word every. So that's for all. For all n in Z, for every integer, if n is not odd, then n is even. Okay, exactly. Every integer that is not odd is even. Is this true or false? It is true. Next example. Here's a statement. Given any two rational numbers, which we'll call a and b, it follows that a times b is rational, meaning the fact that a and b are rational tells you that a times b, which is a new number, a times b, whatever it is also a rational number. The way we express this in logical notation is as follows. For all a comma b in Q, meaning take any a and b in the set of rational numbers. So for all a comma b in Q, a times b is an element of Q. Now, is this true? False. Well, it happens to be true. It might not be so obvious. We'll learn how to prove this in probably next week or the week after. Probably next week, actually. Okay, so that's another example. Okay, next example. There exists a subset X of the natural numbers for which the cardinality of X is equal to 5. In logical notation, this is, there exists an X that is an element of the power set of n. There exists an X in the power set of n, meaning X is a subset of n, such that the cardinality of X is equal to 5. Is this true? Yes, it's true. There is at least one subset of n whose cardinality is 5. Here's another example. Every integer is even. How do we express this in logical notation? For all n in Z, n is even. Is this true or false? Well, it's false, obviously. Not every integer. It's not true that every integer is even. Next example, there is an integer n for which n squared equals 2. So this is expressed in logical notation as there exists an n in Z such that n squared is equal to 2. Is this true? No, this is false. Because if n squared would be equal to 2, that would mean that, that n would be the square root of 2, but that's not an integer. Okay, so there's an integer n for which n squared is equal to 2. That's false. Next, given any two rational numbers a and b, it follows that the square root of a times b is rational. Okay, this is expressed as follows. For all a comma b in Q, the square root of a times b is an element of Q. Wait, this is actually false. This is actually false. It might not be obvious, but think about it. Let's say you have a and b as 1 and 2, right? Let's say a is 1 and b is 2. Okay, they're both 1 and 2 are both rational numbers. The square root of 1 times 2, right? The square root of a times b is the square root of 2. which you probably know is not rational. Now, actually, how do you know that it's not rational? Well, we'll see that in about 2 weeks, how we know that. But anyways, you may have heard that it's not rational. At any rate, the point is, so that shows you that it is not true that given any two rational numbers a and b, it follows that the square root of a times b is rational, because I just gave you an example where I have two rational numbers a and b, and the square root of a times b is not rational. Okay, so the statement is false. Okay, now we're going to talk about nested quantifiers. So where we have for all there exists, or there exists for all, and we'll see many examples. So let's see. So consider the following statement. For every real number x, there exists a real number y for which y squared is equal to x. Again, for every real number x, there exists a real number y for which y squared is equal to x. So let's translate this to logical notation. For all x in R, there exists a y in R such that y squared is equal to x. Now let's ask, is this true? Is this true or not? So it works for some values of x. So for example, if x is equal to 9, okay, so if x is equal to 9, so what is this saying? This is saying we have some value for x, and y squared, there exists a y that's a real number such that y squared is equal to x. Well, if x is equal to 9, then we can say y is 3, and that works, right? So 3 squared will be equal to x, will be equal to 9. Okay, so that it works for some values of x, but the statement says that this works for all x in R. That for all x in R, I can find a y in R such that y squared is equal to x. But what if, for example, x is equal to -9? Right, that's a real number. -9. It's an element of R. So what if x is equal to -9? There is no number y such that y squared is equal to -9, right? Because anything squared, any number squared, is always going to be 0 or positive. It's never going to be negative. So there is no number y such that y squared is equal to -9. So if x is equal to -9, it fails, right? It fails for that situation. And yet the statement claims that this is true for all x in R. So what do we see? So there exists a y in R such that y squared is equal to x does not apply to every x in R, even though it applies to some x in R, like when x is equal to 9. So it applies to some, but not all. Therefore, the statement for all x in R, there exists a y in R such that y squared is equal to x, is a false statement. Consider the following statement. For every real number x, there exists a real number y for which y cubed is equal to x. So this is identical to the previous one, but instead of y squared, now we have y cubed. So translated into logical notation, we have it as follows, right here. Now, is this true or not? Is this true or not? Well, no matter what x is, it could be any real number, no matter what x is, there exists a y, namely y equal to the cubed root of x, right? So in other words, there is some value y, which is going to be the cubed root of x, for which y cubed turns out to equal x, because y cubed will be the cubed root of x raised to the power of 3, which is equal to x. So this works, right? This statement is a true statement because this is saying that this works for all x, that for all x, I can find a y such that y cubed is equal to x. And that's true because no matter what x is, I can find a y, namely the cubed root of x, for which y cubed is equal to x. So the statement is true. Another example. There is a real number y with the property that y cubed is equal to x for every real number x. Again, there's a real number y with the property, meaning it has the following property. Y cubed is equal to x for every real number x. Okay, here it is translated into logical notation. There exists a y in R such that for all x in R, y cubed is equal to x. Is this true? No, there is no number y with this property. There is no number y with the property that y cubed is going to equal x no matter what x is, right? There is no number y with that property. So the statement is false. Now here's a very important remark. So the example before this was for all x in R, there exists a y in R such that y cubed is equal to x. That was a true statement. The example above here, this example right here, is there exists a y in R such that for all x in R, y cubed is equal to x. That is a false statement. Notice these two statements are identical except that the order of the quantifiers has been switched around. Here we have the for all x in R first, and then the for all y in R. Sorry, and then there exists a y in R. But here in the second one, we have the exist at the beginning and the for all x in R afterwards. The moral of the story is order matters. Okay, let's do a few more examples, and let's talk more about how we interpret. Before we do the examples, let's talk more about how we interpret nested quantifiers. So we'll start with the following. So here's a very generic example. We have something like this: for all x in S, for all y in T, P of x comma y. So what does this mean? It means the following. It means it's really just a way of saying for all pairs of x comma y in S cross T, P of x comma y will be true. Meaning P of x comma y applies to all pairs where the first element comes from S and the second element comes from T. So again, all this says is that P of x comma y applies to all possible combinations of x and y where x comes from S and y comes from T. Let's do some examples. For all x in N, for all y in N, x plus y is an element of N. Okay, what this says is take any natural number N. I'm sorry, x. Take any natural number x. Take any natural number y. Right. So you have now two natural numbers. You have x and you have y. Add them together. So you have x plus y. That sum, x plus y, is going to be an element of the natural numbers. In other words, the sum of any two natural numbers is itself a natural number. This is a true statement. Okay. You can sort of take it as a basic axiom, but you could probably prove it in some way. But but it seems intuitively obvious and clear, right? Take any two natural numbers, right? Any two positive integers, add them together, you'll get another positive integer. Okay, how about this one? For all x in N, for all y in N, x plus 1 is equal to y. So this says take any natural number x, take any natural number y. If you do x plus 1, that will be equal to y. And is that true? So that's not true. So it fails, for example, when x is equal to 2 and y is equal to 4, right? So the statement says take any x, take any y, and you'll have that x plus 1 is equal to y. But here, for example, if we have x is 2 and y is 4, it is not true that 2 plus 1 is equal to 4. So this statement is false. Now let's talk about this. Let's talk about there exists an x in S such that there exists a y in T such that P of x comma y. Let's see what that means. What it means is the following. There exists a pair x comma y in S cross T such that P of x comma y. Meaning there is some value of x and some value of y which make P of x comma y true. And there is some pair of numbers, x and y, such that P of x comma y is true. So some examples. There exists an x in the natural numbers such that there exists a y in N such that x plus 1 is equal to y. So again, this says there is some natural number x and there is some natural number y such that when you do x plus 1, you get y. This is true. For example, let x be 2 and y be 3, right? And then you have x plus 1 is equal to y. So this doesn't claim it's true in all cases. It just claims it's true in some cases. And here is a case where it works. So this statement is a true statement. How about this statement? there exists an x in n such that there exists a y in n such that x plus y is less than 2. Okay, so this says there is some x and there is some y in the natural numbers such that when you do x plus y, you'll get a number that is less than 2. So is this true or not? So this is false. Why? Well, the smallest element of the natural numbers is 1. So no matter what you have for x and y, let's say you even say x is 1 and y is 1, right? You can have both of them be 1. But if you do x plus y, if you do 1 plus 1, it's going to be 2. That's not less than 2. So you always have that x plus y is going to be greater than or equal to 2. So it is false to say that there exists an x and a y such that x plus y is less than 2. Now we get to a mixture of quantifiers, right? So here we have for all x in S, there exists a y in T such that P of x comma y. So what does this mean? So for this, it's helpful to think in terms of like players of a game. Okay, so here's how, this is not from the book. This is really not from any source. This is sort of my own take on it. So you don't have to like it. But so first, x gets picked by an adversary. Okay, so for all x in S, meaning x could be anything that is picked by an adversary. Now, no matter what was picked for x, we can pick a y to make P of x comma y true. But the key point is that the adversary goes first. The adversary picks x, then we have to deal with whatever x they chose and try to find a y to make P of x comma y be true. And what this statement claims is that no matter what x the adversary chooses, we can always find a y to make P of x comma y true. That's what the statement says. So here are some examples. So here we say for all x in n, there exists a y in n such that x plus 1 is equal to y. So this says adversary can choose any natural number x. Then we will go ahead and choose another natural number y such that x plus 1 is equal to y. So this is true. No matter what was picked for x, we can always pick x plus 1 as y, and then it will be true that x plus 1 is equal to y. How about this? For all x in n, there exists a y in n such that x minus 1 is equal to y. What does this say? Well, this says that the adversary can pick any x, any natural number x. Then we will go ahead and find a natural number y such that x minus 1 is equal to y. Is this true? So this is false. Why? Consider what would happen if x is equal to 1. So suppose the adversary is smart. The adversary goes ahead and picks 1, right? Now, if we want to pick y to make it so that x minus 1 is equal to y, we would have to pick for y 0. We would have to pick 0 as y, right? X minus 1 would have to be y. But 0 is not a natural number. So it is false to say that no matter what the adversary picks, we can always pick a y such that x minus 1 is equal to 1. Now, suppose the adversary picks 2. Then we can say y will be 1, and that will make it true that x minus 1 is equal to y. But again, we're claiming, this statement is claiming that it is true for all x in n. But here we show that there's a particular value of x, namely x equals 1, where it does not work. Okay, so therefore the entire statement is false. This entire statement is false. Okay, now how about when we have the quantifiers in the other order? So there exists an x in S such that for all y in T, P of x comma y. What this means is, so again, we're thinking in terms of adversary. So first we get to pick x. Okay, we get to pick x. Then no matter what an adversary subsequently picks for y, P of x comma y will be true. So we go first. We have to be smart and clever in how we pick x. And we claim, or what the statement does is the statement claims that no matter what value the adversary will pick for y, P of x comma y will still be true. Here are some examples. So if I say there exists an x in the natural numbers such that for all y in n, x is less than or equal to y. So this says we can go ahead and pick a special value for x such that no matter what the adversary picks for y, x will be less than or equal to y. Is this true? Yes, it is. Why? Because we can simply pick x equals 1, which is less than or equal to every natural number. So if we pick x equals 1, again, we get to go first. So we can pick x equals 1, and then no matter what, I shouldn't say we get to go first. It's not an advantage to go first here, right? It's not an advantage because it's not like, yeah, it's not an advantage to go first. But the point is, I have to go first. But even though I go first, I can pick x equals 1. Right? I can pick x equals 1. I can pick whatever I want for x. So I pick x equals 1, and then the adversary goes ahead and picks anything they want for y. But no matter what they pick, since they're picking a natural number for y, x is going to be less than or equal to y, because 1 is less than or equal to every natural number. Right? Even if the adversary picks 1, right? Let's say I go ahead and pick 1 as x, and then the adversary goes ahead and picks y as picks 1 as y as well. Right? They pick 1 as well for y. It's still true that x is less than or equal to y. 1 is less than or equal to 1. Next example. There exists an x in n such that for all y in n, x plus 1 is equal to y. So this says we can go ahead and pick a natural number x such that no matter what the adversary picks for y, x plus 1 is equal to y. This is false. There does not exist an x with the property that x plus 1 is equal to y for every natural number y. Right? There's no way to pick an x in advance so that no matter what the adversary picks for y, x plus 1 should be equal to y. Right? Maybe I'll pick 3, for example. Okay, but maybe the adversary will pick 17. So in other words, the adversary goes second here. So that puts me at a disadvantage. All right. So anyways, that's the topic of quantifiers and nested quantifiers. And there are many examples in the homework. So hopefully you get a lot of practice for that.